Okay, so we kind of just discussed confidence intervals, and almost kind of parallel to confidence intervals is the idea of the hypothesis test. They're both like doing similar things. We're taking a sample mean, so we're taking x bar, which is our sample mean, and the samples we have a sample standard deviation. And we're trying to make some sort of inference on the population mean mu. And we did this in confidence intervals by kind of getting some sort of a range, possible range for you. Now here with hypothesis testing, it's a little bit different. What we're doing is we're actually trying to prove if mu is a certain value. So let's think of our example with the Black Friday shopping. And remember, we were recording, the hours of shopping, the average hours of shopping. We took a sample of shoppers and then, asked them how many hours they shop. So the average hours of shopping. And we just find several things. So this is just kind of a reminder from your business stats. You've got H0, which is your null hypothesis. And this is kind of almost like the current state. And you've got your HA, which is your alternative hypothesis. Which is what you're kind of trying to prove. So imagine, just think, a non-mathematical example. If you have like an NFL football game and you have a touchdown awarded, then you assume that the touchdown has been scored. But you've got like an instant replay and you're basically using evidence, using video evidence to show that a touchdown was not scored. Now, we're going to be dealing with like the simplest possible type of hypotheses, which is the hypotheses on a single mean. And we've got different ways of doing it. So imagine that we assume, based on maybe past information, that our mu is going to be 5, like the hours shopping. But somebody says, okay, I think it's more than 5, or I think it's less than 5, or even I think it's different from 5. You can set up the hypotheses like this. This is what we call a one-tailed test. We're looking in one direction. And basically, we're going to be saying that the mu, our null hypothesis, our state of being is mu equals 5. And we can either say, if we're trying to show that it's more than 5, we'll say mu is greater than 5. Or if we think it's less than 5, we're trying to prove it's less than 5, we'll say mu is less than 5. And this guy here, the 5 in each of one of these instances, we call that mu0. We could also have a two-tailed test. And in this case, we're just trying to show that it's not equal to 5. Sorry, that's a HA. My A's need to look different than my 0. So my HA is mu is not equal to 5. Okay, so how do we do that? Well, we just want to see how close, this is our mu0. We want to see how close my actual x bar is to my mu0. And what we do, we're not going to do any math for the moment, is we're going to say we're going to have something we call the rejection area. And what we're going to do is we're going to take our sample x bar and say, for example, my x bar is here. So maybe this was 5 and this is 5.1. We'll basically say, hey, you know, this is kind of close enough. We don't have enough evidence to reject. So here we'd say fail to reject. But imagine our x bar gets bigger and bigger and bigger and bigger. We're getting more and more and more evidence. And eventually we say, yeah, our x bar is big enough. Maybe our x bar is like 7. And then we say we're going to reject. So we conclude that mu is greater than 5. And we failed to reject, so we have no evidence that the null hypothesis is not true. So that's just kind of thinking of it very simply. So let's just clear this. And let's just think of it a little bit more mathematically. So we had our sampling distribution. Now what we assume if H0 is true, then the mean of the distribution is actually mu0. And with as a sampling distribution, so we assume that the standard error is sigma over root n. Now, so what we do is we actually transfer this to, we have an x bar. So this is our sample mean, which we found. And what we want to do is we want to transfer it to a normal distribution with a mean of 0 and a standard error of 1. And we do that, and we call the translated version z. And so what do we need to do? Well, we need to, if we need mean of 0, our mean is mu0, so we subtract mu0. And our standard error is sigma over root n. We want a standard error of 1, so we just divide by sigma over root n. And that's the z-test that we cover in class. So what do we do for the different types of hypothesis? Well, so these we kind of have, that was our what we call the test statistic. So we have our test statistic. Of z equals x bar minus mu0 all over sigma over root n. And again, we don't normally know the population standard deviation, so we have to use S. Now this is actually a 0. It's a very bad 0, but it's a mu0. Okay, so if we have a one-tailed test, and we say it's an upper, now remember the z's basically correspond to areas of the normal distribution. And we want some sort of a standard, which is like, you know, we go further and further and further until we reject. how do we define that? Well, we define it with what we call the type 1 error, which is our alpha. And basically, the further we get, the lower the type 1 error, so the smaller the alpha, the further that we actually have to get to reject. So kind of the stricter the test we are. And this is really just kind of given. This is just the kind of the chance. So let me just define the type error. This is kind of the chance that given H0 is true, we actually reject the null hypothesis. So we shouldn't reject, but we reject. And that's just kind of controlling the strictness of the test. You know, it's like we can never be perfect. If we set the type 1 error too low, we'll never actually reject anything. But if we make it too big, then we're probably going to reject a lot of times when we don't need to reject. So, you know, the thing is about, first thing about statistics, it's not perfect. We also, which we're not really going to use in this class, but for completeness, we have a type 2 error. And here we have HA is true, so it's the opposite, but we fail to reject. Now that's a little bit more complicated because say our actual mean was actually 5.5 and our actual mean equals 6, then this actually gives two different type 2 errors. So the type 2 error depends on how different HA is from H0. And you can do things, you can actually have what we call curves of type 2 errors. Now, we don't really need type 2 errors very much in this class, so we're just gonna stick with the definition. Okay, so finally, what we're gonna do is we're gonna, you know, do we accept or reject? So we kind of have, let's just do our one-tailed test. And I'm going to kind of give you this first. So we have the alpha out here. The alpha is the area. And this is usually standard. This is usually 0.01 or 0.05 or 0.1. So this is kind of the strictness of the test. This is my Z alpha. And as I recall to any of your engineers who've done more mathy courses, sometimes we'll do from left to right. So we'd actually, rather than giving the area to the right, we'd give the area to the left. Then it would be Z1 minus alpha. But I'll stick with what we used in the business stats textbooks. And basically, if my Z-score is kind of gets bigger and bigger and bigger, my Z-score hits Z alpha, we've hit our type 1 error threshold, we reject. So we're going to reject H0 if my Z is greater than my Z alpha. So another way of actually doing this is, let me just use a different color. Say I have my Z-score here, then the area to the right is called the p-value. And the p-value is just basically the area in the H0 distribution that's more extreme than your test statistics. And look, alpha's an area as well, and we're going to reject at this point here at the Z alpha where the area is alpha. So we can also say reject H0 if my p-value is less than my alpha. And this is what we'll kind of be doing in this course. Because if you recall back to business stats, we'd usually use the Z-score. We'd go to the tables, we'd calculate the Z-score, And sometimes we'd actually convert the z-score to a p-value using those tables. But this is actually just because the p-value is the same for every statistical test and the concept's the same, this is actually an easier way of doing it. Now, let's just do the lower. So if we've got a one-tailed lower where we're checking if it's less than mu0, so this is my 0, and say we got my z, and here we have my minus z alpha. So again, we've got our z, we go left, 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 and eventually we reject, and this is where we can conclude the HA, which is the mu, in this case, is less than mu0. And so basically what we're doing again is it's exactly the opposite, reject H0 if z is less than, basically it's going to be z alpha, kind of minus z alpha. The thing is actually symmetric. But again, let's just get the blue pen back. Say we have a z-score here. This is the p-value, the area to the left. The p-value gets smaller and smaller and smaller until we hit this area where alpha is to the left. So we reject if p is less than alpha. You notice the advantage of using the p-value. We're using exactly the same rejection on the two different tests. And then finally, we're going to get to a two-tailed test. And this I'll write out. This is the kind of the most important. So we have the 0 in the middle. Now we still have the alpha rejection region, but we have to split it into two. So here we have alpha over 2. And here we have alpha over 2. And basically our z lands somewhere. And if it's anywhere in this area, then we fail to reject. We only reject in these areas. And so that's going to be minus z alpha over 2. And this is going to be z alpha over 2. And so we're going to reject H0. If the absolute value of z, this is just so we've got both left and right, is greater than z alpha over 2. Now the p-value is a little bit different. Say we have a z-score here. Remember, we define the p-value as the area more extreme than z, but also this is almost like a mirror image, that we also have this area more extreme. So the p-value is essentially the p-value you see when you look at R is basically both sides. If you worked it out on one side, you'd have to double it. But we won't worry like that. R will give you a p-value, and R will usually give you like the two-tailed p-value. So if you want to do a one-tailed test, you'd have to divide it by 2. So again, we reject H0 to conclude that it's different from mu0 if p is less than alpha. So I'll just put a note in R. You'll get the two-tailed p-value. We'd need to divide by 2 to get a one-tailed. Okay, so let's now go to R. So again, I'm going to set up the hypothesis. I'm going to do exactly the same as I did before. I'm going to set up the hypothesis. We're going to do it like manually, as you would have done it in business stats. So we set the mu0, and then I'm going to show you how we're going to do it in this class. So the mu0 is 5. I set my alpha, the strength of my test. Now I calculate the z. So it's just the mean. It's my x bar. That's my x bar. minus mu0 divided by the s, standard deviation, over the square root of n. Now again, n is just the length of the vector. So that's my z-score, which in this case is 2.41. Now the rejection region, this is basically Q norma. Remember, this is how we get our z-scores. And because R works from left to right, this is going to be 1 minus alpha over 2. So we're and that's 1.95. You might remember that from business stats. You kind of round it to 1.96. If you've got a two-tailed with alpha equals 0.05, it's plus or minus 1.96. Now, just this is actually looking a little bit complicated, and I can kind of you won't really. I'm not going to be testing this particular bit of code, but literally, if you're to the right, then what all this code is saying, if you're to the right, if you're greater than 0, then we look to the right. If we're less than 0, then we look to the left. And all it's saying is we're basically taking given our z values, we're taking the minimum of this and this area. We're taking the small of the areas. Because if we're less than 0, we want to test to the left. Otherwise, we want to test to the right. So we take the minimum, and p norm gives you a probability from a z-score. If you're getting very worried now, I said again, when we do this in the exams and the homework, I'm just going to ask you to do the statistical test. This is purely to link to business stats. So we have our b value. And sprintf just helps us format. So this formats our z-score, and it basically says question mark is where we put the number, and we do it to 4f. We give it so I'll just show you, we give it 4 decimal places. And then we do the same again. Whoops. Oh, did I actually do that? So I say what the critical is. Then I say, do we reject or not, based on the previous thing, and reject equals true. This is all we're doing is reject is true or false. So we're actually converting that into text. And then we actually write the p-value as well. So we're saying, hey, we've got 2 ways of doing this. My z, the absolute value of z, is greater than 1.96, so we reject. And also my p-value is less than alpha, so we also reject. And then I do exactly the same for a test where the mu is 5.5. So the first one we rejected, but now it's actually a harder hypothesis because our mean is 6, but our mu0 is 5.5. We're trying to show that it's actually different from 5.5. And this time my z is much smaller and my p-value is much larger. Okay, so now we're actually going to kind of do the t-test version, and I'm going to show you how to do it manually, and again then I'm going to show you how to do it in R. Okay, so we did the t-test, the z-test, now we've got to do the t-test, and I'll do this much quicker, as it's like exactly the same kind of idea. So if we have a t-test, and again, it will actually, because of the fact the t distribution converges to the normal distribution, if we have, it will actually work with small n if the underlying data are normal. Or it will actually work with pretty much large n. You can use it most of the time. You assume that the sampling distribution is normal and the t distribution actually kind of converges to the normal distribution. you can pretty much use all the time. And again, I said most statisticians, even with large N, I know you taught a little bit differently in your basic textbooks, would generally prefer to do a t-test. So it's exactly the same as the z-test. So I won't draw a lot of pictures this time because the concept is the same. So we have h0 mu equals mu0, ha mu is greater than mu0, or if we're looking to the left, mu is less than mu0. And we have our test statistic. Rather than going to a 0, 1 z distribution, we're going to a t distribution. So we've got t equals x bar minus mu 0 all over s over root n. And we also have a two-tailed test. So h0 mu equals mu0. ha mu is not equal to mu0. And we also have the test statistic. And that's going to be exactly the same as before. The test statistic doesn't change. It's just kind of where we're looking. And then we have the rejection regions. So for the one-tailed test for the upper, we reject h0 if t is greater than t alpha. Now again, the t distribution as described before has n-1 degrees of freedom. Or if it's a less than, we're going to reject if, I'll put in brackets because the hypothesis in brackets, t is less than t minus t alpha. Let's just see if I can move this up a little bit. So reject if less than t alpha with minus n-1 degrees of freedom. So we can actually draw this a little bit. So a greater than, we have my t alpha, and we have a 0 in the middle, so we're going to reject there. And the less than, we have the minus t alpha, and we're going to reject here. And a two-tailed test as before, we're going to reject h0 if the absolute value of t is greater than t alpha over 2, with again n-1 degrees of freedom. And this time we have minus t alpha over 2. I'm going to move it up a little bit again. And plus t alpha over 2. Okay, so that was a very basic introduction. I kind of skipped through. If I was teaching this in class, in statistics class, I'd give lots of numerical examples, but I want to keep the videos reasonably. As I said, next Tuesday I want to do a little kind of run over statistics for people. So if you want me to give a few numeric examples, I'm quite happy to do that. So going back to the R, so now what we're going to do is, again, we've got the stock screening information. So this is remember, we have the return, which we actually did before, and these are the returns of our stock screeners. So we calculate a t, which is my x bar, the mean of return, minus mu0, all over s over root n. And we're going to do a two-tailed test, so we reject if the absolute value of t is greater than, I said alpha over 2, but here we're going left to right in R, 1 minus alpha over 2 with n-1 degrees of freedom. And the p-value, again, we're just all this is saying is we've got a t. If it's to the left, then the smaller we take the smaller to the left, and the biggest to the right we take to the right. If my t is greater than 0, then we take the area to the right, and we multiply by 2 as it's a two-tailed test. And I think this is so extreme. So that's my t value. 15. Is that correct? Maybe I haven't set my mu0 correctly. Let's try that again. Yeah, 2.7. I think I hadn't updated mu0 from the previous example. So let's go through this again. We do the rejection of the p-value. And then, as before, we just kind of print them out. And here we say our t is 2.7. So that's kind of greater than the mu0. That's showing we're to the right of the mu0. The critical value of t, the t alpha over 2, is 2.17. So we reject, and our p-value is 0.0185. So in fact, if we were using a strict test of alpha equals 0.01, we'd fail to reject. Now, if we do it with mu equals 10, we can see that we're much closer to the mean, and now we get this really high p-value, and my t is 0.03848. Now, what you're going to have to do is we're going to run the t-test. So if we look at the returns, and let's do a t-test, and this automatically is a two-tailed t-test unless you specify otherwise, and it's all done. So you get you actually get the sample mean. Our x bar is 10.8, and you get the t value 2.7, and you get the p value. So you can actually do it yourself then. You actually say, okay, my alpha equals 0.05. I'm going to reject the null hypothesis. My alpha equals 0.01. I failed to reject the null hypothesis. And then we can do the same for mu equals 10, which you see is really close to the sample mean. And this time we're really close and we fail to reject. So very easy. My null hypothesis, let's just write this down. So this is kind of the most important thing. So let's do the first one. My null hypothesis is mu equals 5. My alternative hypothesis is mu is not equal to 5. So actually, and we're going to set our alpha, our type 1 error is 0.05. And what we're going to do is we're going to reject H0 if P is less than alpha. My P is 0.0, let me look back, is 0.0, we'll go back to the mu equals 5 example. My P equals 0.0185. Which is less than 0.05, so we reject H0. So we can say, you know, there's evidence that the mean return of these screeners is not equal to 5. Okay, that's all. And, you know, if you guys are kind of pretty much know all of this stuff, then, you know, just kind of go through all the R code. Because we probably won't be doing a lot of testing of this type in this class, but we will be doing a lot of like interpreting of p-values once we get to kind of more complex techniques.